All right. So let me give you the basic tools that you need to be able to write a proof. The first that we need to encounter. So today's our first class. As I said before, even though I said to record, let me say it again. We're going to have assignments, tests, and the final exam. Assignments will take up 20% of your grade. The tests will take up 40, and your final exam is the next 40. So tests 40. Those will be sectional tests. I don't give quizzes. So you have assignments which you do over the weekend. You have your tests, which are about 13.33% each, and your final exam will be 40% of your grade. The outline will have the textbook. It's called College Geometry, a Discovery Approach, and it's written by David C.K. If you didn't catch that, not to worry. I'll post the outline. I should have posted it before I forgot to post it, so I'll post it this evening. So College Geometry, a Discovery Approach. And we're doing chapter. If you want to get it, it's not a requirement. You don't have to have it because I give the notes that you need. But if you want to look at it for different types of questions, it's not a bad idea to get it, but it's not a requirement because you only use about 5 or 6 chapters out of it. And the book is about 15 chapters. I think. Let me double check. If I'm not mistaken, it's the wrong thing. Oh, it has 7 chapters. And we do 5. Okay. I thought it had more. All right. Yeah. That's the basic revision of last class. So I didn't go in and start any notes or anything last class, but I'm going to start it today. All right, last class we had 1 student. Now we have 1 again. I suppose 1 more might come later. All right. So the first that we need to look at is how to set up a proof. What approach you should take for mathematical models that you're proving. So I'm going to give you the basic setup right here. Now, for the types of proof that we'll be using, they are called, what do you call them? If-then statements. So you're going to be given a statement, which is, you won't necessarily see the word if, nor the word then, but the setup will be like that. So let me, proof, introduction. So not to worry, this course is generally, general has a good pass rate. The only difference is the type of grade that you get. But most people pass it. But if you want to get an A, it's not hard. As long as you get your work done and understand what is being taught, it's not hard. It's easier than most of the math courses. All right, so the first thing we need to know, so we have some statements to call them if-then statements that we need to prove. If-then statements. Oops. Now, these if-then statements, the if part, so whatever comes after the if, is what you call your hypothesis. Oops. And what comes after the then is your conclusion. So it's like, for example, if the shape is a triangle, then it has 3 sides. So you're hypothesizing that the thing is a triangle, and your conclusion is then that it will have 3 sides. Now, there are some statements which are, to be true. You don't have to prove anything. But like if I give you an if such and such, then this, you need to prove it based on what we know before. And that's the foundation of geometry. What we did was we built on stuff that we knew before. Like you show something to be true, or you accept it as truth without even proving that it was true. You just accept it to be true, and then you use that to build on what you want to prove later. Matter of fact, let me give you some things that you're going to encounter. You're going to encounter some words called axioms, or some statements called axioms. These are accepted as true, but were never proven to be true. Just accepted globally or in the mathematics community as a true statement. One of them, for example, is that a line is a what do you call it? Combination of points. So you combine some points together and I get a line. The next one is that a line is straight. Nobody has ever taken up the thing to prove that if it's a line and it's a straight, then it's straight. We just accept it to be true, but it was never proven in any logical, mathematical way. So axioms are statements accepted as true without proof. So statements, you know what, I'm not going to write all this. Let's write the first part. Statements accepted as true without proof. So the first thing we're going to learn in geometry is axioms, because the first 5 rules that geometry is based on were started with axioms. We'll get to that maybe next week or the week after. Maybe next week. Without proof. You're going to encounter a lot of them. You're going to have axioms, you're going to have theorems, you're going to have lemmas. I'll just mention axioms and theorems right now. Theorems, because we're going to have a lot of those in this class. Both of these, axioms and theorems. I think the first 15 rules are going to be axioms and theorems. Then you're going to have lemmas and so later on. So theorems are proven statements. So I'll just digress a little bit, but I want to make sure that when I start using these examples, you know what they're referring to. And they don't have to be mathematical either, axioms nor theorems. But in what we're going to study, we're going to encounter axioms and theorems. So now you know what axioms are. They're accepted as true, but they were never proven back in the day. And theorems are statements that are proved. For example, we know that a triangle has angles that sum to 180. How do we know that? You just, from you were young, you heard about it, but you don't know how they proved it. It was a long method that they used to prove that, you know. We accept it now as gospel. But how we know it's always going to be 180 degrees inside there? But because we know this and this and this must add to 180. But how do we know that to be true? How do we know it's not 185 or 179? So those are things that we're going to show in this class, how they came up with these proofs and conclusions. So we're going to go through the history of geometry. Actually, that's what we're doing. All right. I'm not digress any further. We're going to go back to the if-then statements. Now, the things you need to know about the if-then statements. Let's see now. There are different ways to write them. So let's say we have a statement P. P represents a whole statement. And then you say it implies Q, a next statement. For example, P could be the car is red, and then Q could be Q could be it is fast. If you put them together, P implies Q. It's saying if the car is red, then it is fast. So you have different things that P could be and the Q could be. I'll give you examples soon. I just want to make sure you understand that this represents a statement, the P, and the Q represents a different statement. And once you put it together as P implying Q, you mean what you're saying is if P occurs, then Q will occur, or then Q is true. Different ways to say it. So if P, then Q, this P imply Q right here with arrows, that's a short way of writing it. So P imply Q actually means, so when you see that arrow thing there, it means if P, then Q. That's a short way of writing it. And next way you could say it is if the statement P is true, then the statement Q will occur, or the statement Q is also true. Or if P occurs, then Q will occur, and so forth. If it's a bit confusing, not to worry. When you see the example, you say, oh, that's what Sarah was saying, not to worry. But before I get to deeper stuff, there are 3 words that I want us to get familiar with from the if-then statements. If you have an if-then statement, you can find its inverse. You can find its converse. And you can find its contrapositive. So I'm going to go through these 3 words and give you examples of what I'm talking about. All right, so we have inverse, we have contrapositive, and we have converse. What are these words saying? All right. In math, you have something called the negation of a statement. So it's like negative and positive. It's like not quite the opposite, but it negates it completely. For example, if I say that P is the statement, what's a good one I can use? It is raining. It is raining. Then the negation of P, which is symbolized with this little squiggly thing in front of the P. If you look on the keyboards, you will see like a squiggly line. That means negate. So negation of P is saying not P, right? And you're saying that, okay, P is not occurring. And if it is raining, the negation is not, it is sunny. The negation is, it is not raining. And just make sure that is clear. When you're negating something, you're ensuring that it does not happen. You're not saying the opposite. Because if you just say the opposite, it will leave out some stuff. For example, I've asked students, if I say that Q represents the board is white, and I say, what is the negation of that? Most of them say the board is black. But that is not the correct thing. If you're going to negate a statement, you need to completely negate it. The board is black is just a part of it not being white. For it to be negated completely, you need to say the board is not white. It could be blue, it could be green, it could be yellow, as long as it is not white. So when negating a statement, ensure that you cover everything that it cannot be. The board is, well, I shouldn't say that way. If you're negating a statement, make sure you take care of everything that is possible without that thing not happening. Right. So don't say it is black, or don't say it is clear. It has to be not white, which covers every possibility of it not being white. All right, so now that we know what negation is, I can explain to you what inverse and converse and contrapositive mean. So you're given a statement, a hypothesis with a conclusion. If this, then that. Now, for example, we have a P implies Q. So this is original. The inverse of P implies Q is, sorry, let me start with converse. That one is easier to see. So the converse. So the converse of P implies Q would be, put a different color. Q implies P. So converse is similar to the word reverse. So if instead of going from P to Q, you're going from Q to P. So converse and reverse, you can just think of those two as similar things. So converse is like the reverse of the original statement. Now the one that normally gives trouble because people confuse them is inverse. I'll put by black. Inverse. All right, so inverse is just negating both statements. You're negating the P and negating the Q. So whatever was on either side, just negate both of them. So remember the original is P imply Q enough. So from P imply Q, when you find inverse of that, this is just this one down here. Negate both statements. Negate the left and negate the right. Now the contrapositive, the easy way to remember contrapositive is just thinking of those two things that just happened. The contrapositive is actually the combination of both of them. Contrapositive is this. So you're going to flip it around, find a converse, and negate at the same time. It's going to be not Q implies not P. So the contrapositive is the reverse and negation of the original. So the original would have been P imply Q. When you flip it around and negate it, you get something called the contrapositive. And of these three things, the converse, the inverse, and the contrapositive, the most important one is the contrapositive. And let me tell you why. You need to write this down. If a statement is true, then its contrapositive is also true. Say it again. If a statement is true, the original statement is true. If something, then something, then the contrapositive will also be true. And reverse is also the same. If a statement is false, then its contrapositive will also be false. So the contrapositive is always equivalent to the original in terms of truth or false, true or false. So if the original statement is true, if P then Q, then the contrapositive will also be true. If the original statement is false, then the contrapositive will also be false. To make sure these things are now understood, I'm going to give you some examples, so it can make more sense about what is we're talking about. Is contrapositive and converse and if-then statement. Let me give you examples of all of them now, so we can make sense out of the nonsense. All right. So you've now learned some definitions. We know about contrapositive, converse, inverse, if-then statements. By the way, when you write out the sentence for the if-then statement, I'm mentioning it down here, so you can get everything in one. All right. Let me give you an example. Suppose the P represents. Mute this thing quickly. Get more direction. Yeah. About what happened over the years. That's simple question. Answer that. Muted. You as well. You. All right, good. All right, so P. Let us make P represent. I mentioned this to Renee last class. Oh, she's here. Yes. That means the same thing. There are clouds in the sky. Oh, no. Better one. Sorry. Hope you didn't write that one. I just remember a nicer one. The animal has wings. The animal has wings. And Q. What's that? Oh, thought I was saying something. Renee talking to me? Why? You might have to type what you're saying. You're breaking up badly. I can't hear. I hear your voice, but I'm not sure what you're saying. Can you hear Harold?
Not at all, sir. It's breaking up as well.
Yeah, she's breaking up bad, man. So sorry about that, Renee. You might have to type what you're saying. I'll check the chat. I'm not hearing you. All right. Sorry about that. Oh, I was saying it is a bird. Oh, okay. Not necessarily. Well, yeah. That's true. I think any animal that has wings is a bird, because you have animals that have things that look like wings, but they're not birds. You're right. All right, it flies. So let me show you how the if-then statements work now. So if you get this in a question, I give you in a test, I give you, okay, P is this statement and Q is that statement, and I ask you to write the if then, number capital, right? The if then, and I put this word right here, prose statement. That means to put in words. Meaning, like, for example, I say A is P imply Q. You have to write out if the animal has wings, because the P is the if part, the hypothesis, and the Q is the conclusion. So you'd have to simply say, I'm write the first one for you. If the animal has wings, then it flies. Give the next one, let's say Q, not Q, sorry, B. And I say, okay, Q implies P. That would be if the animal, sorry, if it flies, or if the animal flies, if you want to put it animal, if it flies, then the animal has wings. Now, let me just tell you something right here. One of these statements is not true. Hold on, I'm missing something. Then the animal has wings. One of these statements is false. Let me just make sure this is clear. For a statement, an if-then statement, or any statement really, to be true, it has to be always true. It can't have any error in it. So if a statement is true, that means it is always true. If a statement is false, it is false. If you can find any occurrence in which a statement is not true, then it's a false statement. Let's make sure you understand that. For example, if I were to say, a square is a rectangle, that is always true. A square is always a rectangle, but a rectangle is not a square. You have some instances where a rectangle is a square because, once it has 4 equal sides, it is a rectangle and it's also a square. But a rectangle is also a square sometimes, but it's not a square all the time. So to say a rectangle is a square, that's a false statement. It is true sometimes, but false sometimes as well. But a square is always a rectangle, in case I've had this class before where students don't know what a rectangle is, so make sure that is clear. You understand what I'm saying? So let me give you the criteria for something to be a rectangle. A rectangle, 4 sides, 4 90-degree angles, opposite sides are parallel, opposite sides are parallel, so they're running adjacent to each other. Well, not adjacent, parallel to each other. Parallel. Here's the next thing. Well, I said 4 90-degree angles, so you know it's 360. I don't have to mention that. So it has 4 sides, 4 90-degree angles, opposite sides are parallel, and opposite sides are equal length, yes. Opposite sides have equal length. That's the criteria. Those are all the things that you need for a rectangle. So for example, you have some shapes like a parallelogram. Even though this matches, I didn't draw properly, but you get the idea. A parallelogram, it has, look at it, opposite sides are parallel. Good. I can see that clearly. Opposite sides have equal length. So all the opposite sides, like this side over here is opposite to this one, they have equal length. This one over here is opposite to this one, it has equal length. And as you can see, they're parallel. It has 4 sides. 1, 2, 3, 4. But it does not have 4 90-degree angles. This angle right here is obviously not 90 degrees. It's not a right angle. Nor is this one right here. So it's possible for a shape to fit some of the criteria, but not everything. So parallelograms are not necessarily rectangles. But a parallelogram can be a rectangle, because a rectangle is actually a parallelogram too. It matches everything. It has therefore, well, let me not say that. I said it the wrong way. A rectangle is a parallelogram, so I should have said that. It has the 4 equal sides. Sorry, the opposite sides. It has the parallel, and it has 4 sides and they're parallel, and they also add to 360 degrees. But they're not necessarily parallelograms. But parallelograms. Sorry, what did I say a while ago? Parallelograms are not rectangles, but rectangles are parallelograms. Right. Anyway, back to the square. So these are the criteria for the rectangle. This one in this black box here. For rectangle, it must have 4 sides. It must have 4 90-degree angles. The opposite sides must be parallel, and the opposite sides have equal length. But for a square, it matches everything that is in there, but one more thing is there. Do you remember what that is for the square? You guys should know that. What's the next thing for the square that the rectangle doesn't necessarily have? What makes a square a square? Oops.
All 4 sides are equal.
Right. That is the key. It has 4 equal sides. All the sides are equal. So it has the 4 sides, yes, that's good. It has 4 90-degree angles, yes. Opposite sides are parallel, yes. Opposite sides have equal length, yes. But at the same time, all the 4 sides are equal length. So not just opposite. All the 4 sides have equal length. So you see, all the squares fit the criteria for the rectangle, but not vice versa. The rectangles don't necessarily have to have equal length. So because of that, we can hope I can draw it properly. Looks squarish. Well, I mean, I'm supposed to have curved sides, but where's the regular rectangle? Oh, here it is. So here's a rectangle. And then let me see if I can draw a square. That's what 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So right here. Yeah. Here we have a square. So you see the square has equal length on all sides. So all squares are rectangles, but not all rectangles are squares. So it is true to say if it is a rectangle, beg your pardon, if it is a square, then it's a rectangle. That's always true. It is not always true to say if it is a rectangle, then it's a square. This thing down here is a rectangle, and it's a square. Seems true, but look at the one above. This is a rectangle, but it's not a square. That will make the statement false. So if a statement is true 99% of the time and false in one occurrence, it's a false statement. All right, so that's just an example of how you can tell if a statement is true. For it to be true, it must be true in every possible way. Please remember that. And if it is false in even just one way, then it's false. If you can find one occurrence where it is false, it's a false statement. Let's get this out of the way. Go back up here. All right, back to the statements now. So let me ask you guys now. Is A always true, or is A true? If the animal has wings, then it flies. Is that a true statement? What do you think?
Thinking, sir. I'm thinking.
Go ahead.
It can have wings and not fly.
Which example? Give me an example of that.
I'm coming, sir. The only thing I can think of right now is dinosaurs, but
Well, we have to prove that they existed first. All right, let me give it. You're on the right track. Wait on what? So is based on what you're thinking false or true?
I'm thinking false because the animal can have wings and not fly.
Right. So you're correct. No, it is false. Let me give you an easy one. You know the animal called ostrich?
Oh yes, that's it.
All right, that's one of them. Penguin as well.
Yes.
There's a penguin, you have ostrich, you have emu. Those are 3 examples of birds that have wings, but they can't fly. There's still a verdict out on the chicken. Some people say it can fly, some say it can't. I don't know.
It can fly. That is one, so it only jump high.
Right, jump and might float for a little while, but it won't fly. So emu, ostrich. All right, since you agree with chicken, put chicken in there. So these are examples of animals that have wings but cannot fly. But the ostrich and the emu, they can run very fast though, faster than us. All right, so there's an example of a statement that is true sometimes but false sometimes as well, or true most of the time. So because it is not always true, it is a false statement. Can I hold here? Yeah. So those are examples of animals that make this statement false. They have wings, but they can't fly. All right. What about the other way around now? If it flies, then it has wings. Is that true? Do you know any animal that can fly but doesn't have wings?
I think this one is true because you have to have wings to fly. I can't think of any that flies that doesn't have wings.
That is correct. There's no animal that can fly without wings. Let's get this out of the way. Kind of squinched up. All right. Yeah. So if it flies, then the animal has wings. That is true. This is always true. There's no example of animal. There's an example of a lizard. Is it lizard? There's a certain animal that can glide. Like it jumps off and glides down, but it doesn't fly. I don't remember the name of it anymore. It's called
Oh,
there's a
yeah.
special lizard as well.
Yes, Is not the chameleon. It's yeah, I see it already, sir. It doesn't fly, but it glides.
Right, right. And there are more than one of them. There's a squirrel that can do it, a type of squirrel or some rodent can glide, but it doesn't fly. All right. So once the animal can fly, then it must have wings. So that's an example. Those are two examples of statements that are always true and true sometimes. Remember, if you can find one example of a statement not being true, then it's a false statement. So don't think of the majority, think of all the time. All right. So let's do some converse and we call it contrapositive as well. So look at this now. Let's say general things before that. Let's do not P implies Q. Let's do the next one. Not Q implies P. And then converse would be converse of the P imply Q would be Q imply P. Oh, that's already. The converse already right up here. And just label them. So this one was the converse of the original, P imply Q. Let me just negate both of them now. Not P imply not Q. Going to check if it's true or false. And last one, not Q imply not P. All right. The not P imply Q is saying if the animal does not have wings. I'm going to write it out this time, but next time when I'm giving examples, I won't write out everything. So if the animal does not have wings, even though I'm not hearing you, Renee, can you hear me? Are you hearing me clearly? Oh, she's gone.
Me talking there?
Oh, I can hear you clearly now.
Yes.
Yeah, you're good now. Okay. I'm just checking if you can hear me.
Yeah.
Okay, good. All right, so that's the if then statement, pro statement for the not P imply Q, for not Q imply P, if it does not fly, then the animal does not have wings. Oops, spell that wrong. Aminal. And the animal does not have wings. Second to last one, if, you know what, I'm going to be lazy now. This is the other writing. Duplicate it. Carry it here. All right, so it says if the animal does not have wings, then it does not fly. Okay. But I can delete that. Because it should be, then it does not. Wait, I haven't even tested you guys. The last one, what is it saying? Not Q imply not P. What would that be? If what? Anybody hear me? The last statement down here.
If it does not fly, the animal does have wings.
All right, so one more. I heard the first part. They said if it does not fly, what?
If it does not fly, the animal does not have any wings.
All right, good. That's correct. So if it does not fly, then the animal does not have wings. Lovely. Wait. Oh, I made a mistake down here. This one was, I wrote it up here, but I wrote the wrong thing. So good thing I said that. Then the animal has wings. For D, I made a mistake. It should have been the animal has. Then the animal has. Oops. Oh, then what I should have done was, put that back. Put that back. I can't. Okay, yes. Let's copy that one. Or better yet, switch them around. Make it the not Q, not P. So put this one as a P then. All right. So if the animal does not fly, then the animal has wings. For the last one. All right, let's check the validity of the statements now. So we conclude that A was false, B was true. What about C? Do we think this statement here is true or false? Not P imply Q. Is that true or false? Well, I didn't put P imply not Q. Should I put that one in? Anyway, so if the animal does not have wings, then it flies. Let's check this out. That is very false. Dogs don't have wings, dogs don't fly. This is saying if the animal doesn't have wings, does not, then it can fly, which is a false statement. Very clearly false. There's no animal that doesn't have wings that flies. So it's false. For the fourth one, if it does not fly, then the animal does not have wings. So this is saying once the animal cannot fly, then the animal doesn't have wings. And we showed that to be false before. Remember, if you think about it very carefully, think about this must be true first. The animal doesn't fly. All right? So it's saying if it doesn't fly, then at the same time, it means it does not have wings. That is not true. Because the penguin does not fly, but the penguin has wings. That's an example of it not being true all the time. Because this statement is saying once it doesn't fly, they're not supposed to have any wings. But we know of animals that do not fly, but they have wings. So this is also a false statement. And before I go any further, you see, because P imply Q was false, then not Q imply not P has also to be false. Why is that so? Let me show you again. This statement right here, this one down here, the not Q imply not P, is the contrapositive of the P imply Q. The not Q, matter of fact, let me circle them permanently. Not Q imply not P is the contrapositive of P imply Q. Meaning we negated them and turned them around. So we found the inverse and the converse at the same time. We flipped it and found the negation of both statements. Once you do that, you're finding the contrapositive. And as I told you before, if the statement was true, its contrapositive must be true. And also, if the statement was false, then the contrapositive must also be false. So we didn't even have to check it out, think about it logically. Once this one was false, then this one has to be false as well. That's how contrapositives work. Which is a good way to test if you came to the right conclusion. Because if you came to a conclusion about a statement and the contrapositive is giving you a different result, something is wrong. Because if one was false and the contrapositive is then true, maybe the first one was true as well. Or the one that you've just thought about was actually false or true, whatever I said before, opposite. So they must always have the same validity. If one is true, the next one must be true. And if one is false, the next one must be false. Contrapositive. All right, let's check the next one. I'll give you guys some work now. Not Q imply not P. This business here. Is this true or false? If the animal does not have wings, then it does not fly. Is that true or false? E. We're checking E.
The animal does not have any wings, then it does not fly.
What are our thoughts? True or false?
True, sir. You're not hearing me?
Yeah, hearing you now. You said true?
Oh, sir. Yes, sir.
That is correct. That is always true. Because as even I think what Harold even said it before. Harold said there's no any animals that don't have wings that can fly. That's what that is saying. If it doesn't have wings, then it cannot fly. So for it to be a false statement, it would have to be proven that an animal can fly without wings, and that's not possible. It's saying if you know an animal that doesn't have wings that can fly, then it is false. But this is saying if it doesn't have wings, then it cannot fly or it does not fly, which is always true. A matter of fact, a requirement for flying is wings. You can't fly without wings.
Yes, sir.
All right.
So in a way, it is saying that it has to have wings to fly if it
Correct.
twists around.
Right. That's what it's saying. A matter of fact, if you think of it, if you realize it, look at it carefully, and put it in blue this time or green. This statement this time is the contrapositive of something up there that we did before. Look at the previous statements, A, B, C, D. Which one of them is a contrapositive for this one down here? Which of them you flip around and negate to get this one down here?
Yes, sir.
No, not A. A was contrapositive for this one. This one's the contrapositive for one of these right here. A, B, C, or D.
If it flies, then the animal has wings. So it would be B.
Correct. If you flip around B, put the P in the front and negate both of them, you get E. So B is the contrapositive of E, and vice versa. E is the contrapositive of B as well. So you notice that B was true, so E had to be true as well. That's how contrapositives work. Once the statement is false, the contrapositive is false, and once the statement is true, the contrapositive is true. So you get two examples of contrapositives right there. Both of them were logically equivalent, meaning if one was false, the next one was false, and if one was true, the next one was true. As you can see, A was false. If you negate the P and the Q and turn them around, you get E, which was also false. Oops. You get D, you get D. Negate the P and the Q and turn them around, it ends up with D. And both of them were false because they are contrapositives of each other. They have to be false alike or true alike. And B, as in boy, the Q imply P. If you negate it and flip it around, not P at the front, not Q at the back, then you end up with D, which is also, what am I thinking? Sorry. What did I say? Oh, yeah, not Q, not P. You put not P at the front, and you put not Q at the back, beg your pardon, you end up with E, which is also logically equivalent. True and true. All right, so since we're getting out of those now, let me move to the last one first. The last one, we didn't have any contrapositives for this one. Oh, we did, we actually did. It's right here. Didn't you realize that? A coincidence. So it's because this is false, this has to be false as well. I don't think I told you before. If you have a not statement like not P, then the negation of that is going to be P. You're not going to write not P. Not P is just P. So if you negate in the negation, you get the original.
Oh, yes, sir.
So, right. So because of that, now these two are logically equivalent. We'll put them in, what color can I use? Blue? Yeah, these two, C and F, are contrapositives. So they should have the same result. One is false, so the next one has to be false as well. So you have to check it. It doesn't know it's false. If you want to check it, let's check it out. If the animal does not fly, then the animal has wings, which is obvious foolishness. The dogs don't have wings, and the dogs don't fly. But this is saying if the animal does not fly, then it has wings. There are only a few animals that are like that. They're up here. Emu has wings, does not fly. Or emu doesn't fly, it has wings. That's true.
And the chicken.
chicken as well, and the penguin, right? Those animals don't fly, but they have wings. That makes the statement seem true, but there are a whole lot more that make it false. Any animal you can think of, lion, bear, dog, cat, all those animals don't have wings, or they don't fly, but they don't have wings either. So F is false, C is false, and there are contrapositives. So I put them in same colors, so you can pick up contrapositives here, and contrapositives here. All right, so hopefully you guys understand contrapositive now because you're going to be using it. There's some trick questions that have the contrapositive, so I want to make sure you understand them. So remember, to negate it and flip them around, you get the contrapositive. If you negate both of them alone, you're getting the inverse. If you're flipping them around without doing anything else, you're getting the converse. So converse is reverse, flipping them. Negating both gives you the inverse. All right, so that is converse and inverse and contrapositive. All right, let me get some light right here. It's a bit dark. Give me a minute, please. All right. Now, the next thing we're going to look at is what we call I think I mentioned it before, but before I move on, I must make sure that it's cemented. The first part, the part that comes before the then. So, like, if you have a statement, look at the first statement there, the part A. If the animal has wings, this part will be referred to as the hypothesis. I think I mentioned it. Did I write it down? Let me go back and see if I write it down. I did mention way up here. Okay, let me mention it again in more detail. So the first part of the statement before the then is called the hypothesis. This part right here. And then right here again. Oops, if it flies, it would be the hypothesis. So the hypothesis is the setting the foundation of what you're going to prove or what you're going to lead it to. So the hypothesis, you assume that that part is true already. So you say, okay, animal has wings. Let's assume that is true. In part B, it flies. Okay, let's assume that animal flies. We know an animal to be something that can fly. So when you lay a hypothesis, you're assuming something that's true, whether it's true or not. You just assume that, okay, let's say this part is true. Will it lead to that? Will you get a conclusion of such and such? So when you're creating an if-then statement, you want to prove it, you are creating a hypothesis, which you assume to be true, assume to have occurred already, and then you come to a conclusion. That's how you need to prove it now. So, okay, if this, then that, can you prove that to be true? That's how they do things in geometry. They will say, okay, if this is taking place, can you prove that that would take place all the time? That's how they lay the foundations to get the theorems and to get the lemmas and corollaries, which you're going to learn about soon. But for this first part, you're going to start with axioms. Not today, but the axioms, as I said before, lead to your theorems and so forth. So when you're proving, you're creating a rule. You create a hypothesis, the if portion, then you prove that your conclusion will always be true. That is how you can come up with rules or theorems. By creating a hypothesis, coming to a conclusion, proving it to be true all the time.
Okay, sir. So that would mean today, reasoning and logic. This is the foundation for the axioms and the other stuff coming up, right?
Correct.
Okay, and what you call that one, lemma? L-E-M-M-A?
Well, no, I mentioned the word lemma. L-E-M-M-A, yes, but it's a lemma is a small theorem.
Okay.
Used to prove a next theorem.
Okay.
So I'll give you the definitions for all of them maybe next week. I could have done it today, but because I don't want to use it yet, I don't want to talk about it now. You have to go back and check it.
No, sir. Okay, when you're ready. I'm just thinking ahead. I'm not in any rush.
Okay, no problem. Cool. All right. Let's give you now. I'm going to show you what time is it. have about 26 minutes. I'm going to show you how to create a direct proof. Like I'll give you something to prove and you want to show you, I'm going to give the outline for it. What you need to go through to create your proof or make your proof there. So let's say we have, let me put it this way. The outline, I'm going to give you the outline of a direct. You have indirect and you have direct proof. And this is what method is going to, that we're going to use is called a column proof. Oops, what happened? Come on, all the way across. All right. So we're going to give the outline, beg your pardon, of a direct proof. All right. So suppose we have proven these things here. Suppose we have proven that P implies Q, that R implies S. Whatever, let's give them some names because we're going to use them right now. Suppose we have proven this, let's call it theorem 1. Theorem 1. We have proven that P implies Q. We have proven the next theorem. We have accepted it to be true, but in this case, once a theorem is proven, we have proven that R implies S, and then we've also proven that theorem 3, we have proven that Q implies R. And you want to prove that P implies R. I want to prove this. Shall I put in red? It stands out. Why is this thing so hard to click? My goodness. Yes. Prove that P implies R. All right. So here's the outline. First thing you're going to do is set up your, what you call your columns. And in your columns, you're going to have your conclusions. We're going to come to some conclusions. Not like what I talk about with the hypothesis and conclusion. You're going to come to some conclusions and you're going to justify your conclusions. So your conclusions and our justifications. So when you're using it, first part of what we're proving, when you're asked to prove something, you're going to set up like this. Pretty simple. I don't even think I need this many lines, but just in case, there they are. So you're going to write number 1. Now, for your conclusion, you will have been given something to start with. Remember that we have told you before. I've told you before that on the left is what you assume to be true. On the right is what you're going to conclude. You're going to prove that it comes to that conclusion. So in other words, you are accepting that this side over here is true, the P. So your first conclusion will be the statement P, whatever the P is. So you know that P is true. So we have P as our first step. How do we know that P is true? It was given right here. We're proving that the P leads to R. In other words, P was given to you. It's like saying, okay, if that shape is a triangle there, prove to me that it has 3 angles. So all right, we know that, okay, we know that P is a triangle. So we have this part right here. We know that P is a triangle. It doesn't make sense to prove something we don't know start off anyway. So we know that thing is a triangle. We know that P is true. So we have P. Your justification is it was given. Most of your proofs are going to start like this. You have the given portion, which is the hypothesis. You start the hypothesis most of the time. Sometimes you won't. But 90% of the times you're going to start with the hypothesis. The thing that you want to prove leads to the next thing. So your P. So if it's like an easy 2 marks, you get 1 mark for this part here, 1 mark for that part here. Don't miss out on that. If you're not sure to start with the given, it might work out anyway. So you're going to start with your conclusion of your hypothesis. All right, you're proving that P leads to R. You have to have the P to go to the R. So P is given. That's the justification. We have P to be true. Now, if you look at the theorems that we have supposed to be true, we have these. We have proven that theorem 1 is this. P leads to Q. Theorem 2, R leads to S. Theorem 3, if Q takes place, then R will take place. So we have assumed that these two, we have been given those to be true. Theorem 1, Theorem 2, Theorem 3. Now, what can we know? What do we know that P leads to? In Theorem 1, we say that P will lead to Q. Remember, those are proven already now. If P takes place, then Q will take place. So in our proof, we can say, okay, if you have P, you will get Q. How do I know that? Theorem 1 said that, or told us that. So it's actually going to say, you're going to realize how easy this is. So say, oh, let me see if you guys catch on yet. What do we get from Q? Look at the theorems. What do we get from Q? Anybody? Did I lose everyone?
I'm sorry, sir. Go again.
If you look at the theorems over here to the right, the theorems that were given to be true, or we have proven already, what does Q lead to?
Theorem 3.
No, but I mean, you tell me where you get it from, but what does Q lead to?
Oh,
Well, P to Q, Q to R, and R to S.
Oh, there you go. Q goes to R. That's what I wanted to hear. So, Renee was answering my second question, which is, how do we know that Q leads to R? Renee, you said it before. Because Theorem 3 said so. That's why we know that.
theorem. Okay.
All right, so Theorem 3. So you're giving me justification. So from Theorem 3, we see that Q leads to R. And then what does R lead to?
S. S.
S. Oh, geez, I'm sorry. I was supposed to prove that P leads to R, to S. I don't know why I said R. Beg your pardon. I was supposed to prove that P leads to S. I
Yes.
don't know why I put that. My mistake. That's why when I'm creating things, I need to be careful. All right, so from P, we got Q from the theorem 1. P led to Q. Oh, by the way, when you're writing the conclusions, you're writing how things are working out. You're saying that P goes to Q. That's what the table is telling us. And Q goes to R. That's what this is saying. This one goes to this. This one goes to that. And from theorem 2, we see that R implies S. So R implies S from theorem 2. Therefore, we have shown that P leads to S. So that's what you call a direct proof. You go from one to the next thing, to the next thing, to the next thing, until you get to what you want. It's direct. Indirect is a bit trickier. I'm going to give an example of indirect with numbers that you know about already. I think I mentioned them last class already, but I'm going to mention it again. So for direct proof, you start from what you know to be true, you go directly to what you want to get to. We have gone straight from P to S. First we went through R, Q, then R, and then we got to S. So P implies S, I should have written, not R. All right. Indirect is a bit trickier. Let me give you an example of indirect so you can understand how it works. For indirect, you need to eliminate all the possible options that don't correlate to what you want to prove. For example, if I want to prove that a number is negative, but I can't go directly to show the negative result, all I have to show is that, okay, it's a number. You're given a number. You can prove that it is not positive, and you can prove that it is not 0. That is enough, you know. If you can show it's a real number, it is not positive, it is not 0, Only thing is left is that it is negative. Because once you're a real number, you have to be either positive, negative, or zero. All right, so that's how indirect proof works. You'll be given something, and you want to prove that it leads to something else, but you can't go directly to the thing. So if that's the case, all you have to do is eliminate all the other possibilities and get to that one thing that you want. Let me see if I can. 50 minutes. I can probably show it to you in time. Let me give you an example of the indirect proof. And then next class, we go through some questions that show you how to prove with the stuff that you're given. It can be tricky, but especially indirect. I'm going to give you examples of all the ones I can find. So I want to be. Oops. Let me just get this out of the way. I like how this one looks. Let me keep it. Copy that. Outline of an indirect proof. All right. All right, so we have done the direct. Let's do indirect now. So suppose we have some stuff again. Suppose we know these axioms and theorems here. We know these. We know that theorem 1 tells us that R implies not P. Not P. Theorem 2 tells us that S implies not P. And we have some possibilities. All logical possibilities we can get. Just like a while ago, all logical possibilities were, if it's a number, it has to be negative, positive, or zero. Those are logical possibilities. In this case, logical possibilities are either R, S, or Q. So we have these things happening here. We want to prove, I'm putting red again, prove that if P, then Q. So prove that if P is true, then Q will be true. All right, so follow up with this one now. This one has some details that I didn't mention yet. Well, I mean, I didn't mention it. But you didn't see them in the direct proof. So we're going to have the same setup. I'm going to have our little table. So I might need some more lines. I'll drop in some, hopefully I'll get enough. Sure. All right. Exactly what to do. OCD then, but I mean. Right, I'm moving. All right, you know what? Make it stay. All right, so we have justifications and conclusions again. So remember, we want to prove that if P takes place, then Q will take place. So we'll start with number 1. P. How do we know P? Because we have assumed that, or we have hypothesized that P will take place. How can you justify that? It is given to us. We need to prove that if P is true, then Q is true. So we have to assume that P is true. Now, here's where it gets a little different. See, a while ago we could go straight from whatever to whatever. You notice that theorems don't have any P. We don't have a P implying anything, P implying anything here. We have theorem 1, R implies not P. Theorem 2, S implies not P. And we have some possibilities right here. From P, we can get either R, S, or Q. Oh, should I mention that? You'll be given some possibilities, or logical stuff. You have a conclusion of P taking place. The P can either lead to R, S, or Q. We want to prove that it goes to Q. Just like a while ago, we have a real number. The real number can either be negative, 0, or positive. Similar setup right here. In our case, we have P. The P can either lead to R, it can lead to S, or it can lead to Q. We don't know which one it's going to lead to, but we want to prove that if the P is true, it will lead to Q. So the first thing we're going to set up is, okay, we can get either R, we can get S, or we can get Q. How do I know that? It was told to us that it was the possibilities right here. So the justification is all logical possibilities, or if you want to be lazy like me, you can write all logical cases. It's going to either go to R, S, or Q. How do we know that those are logical cases? They told us right here. The P will go to either R, S, or Q. So write it down. P goes to either R, S, or Q. What you're going to do right now is show that it can't go to R. You're going to show it can't go to S. So start with R or S, doesn't matter. I'm going to start with R. Number 3. Oops. For number 3, assume it goes to R. So right now we're saying that P goes to R. Why am I saying that? It's the first logical case. I just pick one. If you had pick S first, it doesn't matter. If you even pick Q, we don't want to pick the Q because we can't show Q anything happening with the Q. So we're going to leave it for last. Pick any one of the other 2. If you had 5 cases, pick any one of the other 5, apart from the one you want to go to. So we're assuming R. But look at what happens from R. From R, we get something called a contradiction. Because notice that R is not P. Look right here. R gave us not P. So R will lead to not P. How do we know that? Theorem 1. But that's what we call a contradiction, because look here now. Let me make sure you understand how this thing works. Let's say P meant it is a real number. So we want to prove that if P is a real number, then Q, for whatever Q stands for. But look at what we've come to. We've said P is true, it's a real number. That leads to R, whatever R means. Maybe R means it's a square root or something. So P is saying it's a real number. R is saying something else, but then R went on to say that P is not a real number. Remember P, we assume that P means a real number, right? That's for argument's sake. We're saying P represents a real number. Okay, P is true, it's a real number. We'll go to R next. R saying something else. And then from that R we get not P. So here's what we have so far. Okay, the thing is a real number. It is then R, and then R says it's not a real number. That's a contradiction. Because if you're assuming something to be true, then it leads to something being not true, the same thing being not true. That's what we call a contradiction. And from theorem 1, we're getting that contradiction. You symbolize it or signify it by writing this. 2 arrows colliding. That means contradiction. So whenever you get a contradiction, you write those 2 arrows to show that, okay, that cancels this R business right here. So P can't go to R. because R led to a contradiction. The thing is a real number. R took place, it's not a real number. Contradiction. So we'll go to the next logical case, which is therefore going to be, what was it, S? So we assume S instead. That's the second logical case. Remember, we have three possibilities, you know. It's either R, S, or Q. We try R, get contradiction, get foolishness. The thing was P, but then it says not P. We try S. What does S give us? See if you guys are following. You guys fall asleep on me. Hello? All right, so because the time is going, I'm going to tell you.
I'm thinking.
You're thinking, look up at the stuff that we know already. What does the S go to?
Oh, it goes to not P.
Not P, right. And that is another contradiction because not P cannot take place because we know that P is true already. We have said that P is true from up here. And when you go to S, it gives us not P again, which is a contradiction that we got from theorem 2. So if P is true, it can go to R. We tried R, we got not P. So R can't work. We tried S, we get not P again. S can't work. Because it's like writing this. Make sure you understand. It's like saying P implies R, which implies not P. Foolishness. P cancels not P, or not P cancels P. But we know that P is true, so we can't use R. Same thing for the what do you call it? For the S. S also gives us not P. So if we have tried if we have tried R, didn't work, tried S, didn't work, there's only one possibility left, which was Q. Because Q was our last logical possibility. We don't have anything for Q, but we have eliminated R, we've eliminated S. So all that is left is Q. So we write, therefore, Q. How do we know that? Here's a special rule. It's called the rule of, starts with E. If we had time, I'll ask you guys to give me what you think E is, but I'll say it right now. It's the rule of elimination. Very simple word. We've eliminated all the other two, so the only thing left is that Q is our possibility. So here's how indirect works. You eliminate everything else, leaving only one option, which is indirectly going to that option because you have not proven that it goes to it, But you have proven that the other possibilities can't work. So indirectly, it must have been this possibility. Just like if I tell you you calculate something, the result is a real number, the number is not negative, the number is not positive, so okay, it must have been 0. Same type of thing. You eliminate all other possibilities, leaving only one, which means that you have indirectly shown that start P in this case leads to that result Q, because it's not R, it's not S, and the only other thing that's logical is the Q. Hope it makes sense. Any questions about that?
Okay, I'm absorbing it, sir.
All right, lovely. So I'll give you some time to absorb it after class because we're going to stop right here today.
Okay, sir.
All right, next class, I'm going to give you some other examples, but I'm going to allow you guys to work more with me. I'll probably do one more without any help. And then after that, I'll ask you guys to assist me so to show that you're understanding or working it out. So look it over. I know it's new to you. I think it's new to you guys. If you have any questions, you can let me know next class. All right?
Okay, sir. Only 2 students in this class?
It seems that way so far. I checked the register last time. I think I saw 3. I checked it on Sunday. I'm not sure if I checked the right register, right class, but I'm going to double check it and let you know Thursday. Wednesday.
Okay, sir. Sir, I have you tomorrow again for Cal 2 and one more.
Almost linear algebra.
Yes, sir. That's one. Yes, sir. So I'll see you tomorrow.
Well, they can watch recordings for those because we started those last week.
Yeah, man. I'm going to make sure to watch them before class begins.
Okay. No problem.
All right,
All right,
sir.
Rennie. Yeah, man. Cool.
All right. Take care. Bye, Rennie.
Renee, I don't know if you're hearing us still, but
Bye.
stopping right here. Oh,
Yeah,
you're here.
man,
Okay.
I'm hearing. All right, bye.
Bye bye.